Ohm's law, macroscopic form and resistance. Let us consider a conductor of length L and area of cross section A. It is connected to a battery of potential difference V. Now this battery set up an electric field E and constitute a current I. Consider a segment of wire of length L and cross-sectional area A. The microscopic form of Ohm's law is J equals sigma E, where J is the current density, sigma is the electrical conductivity, E is the electric field. We consider this field is uniform. Then let us substitute what is J, sigma and E. J equals I by A. The current density is the current flowing per unit area normal to it. Then sigma, electrical conductivity, is the reciprocal of electrical resistivity. The electrical resistivity is given by a formula M divided by N E square tau. Here, all the term on the right hand side are the parameter of a material. For a given material, the electrical resistivity is a constant. But as we increase the temperature, the frequency of collision increases, the relaxation time decreases, then resistivity increases. Electrical field is the negative potential gradient of potential gradient. So in a scalar form, we can write in general form E equals V by L. So as we substitute all these three formula in the formula, we get instead of J, I substituted I by A, instead of sigma, I substituted 1 by rho, instead of E, electric field, I substituted V by L. Let me rearrange this. I get V equals I times within bracket rho L by A. Here, V is the potential difference and I is the current. Now, what is there in the bracket rho L by A? Right? This is a factor. This quantity rho L by A is called resistance of the conductor and is denoted by a letter R. So let me write what is R here. R equals rho times L by A. As we know, rho is a parameter of a material. Then R directly proportional to the length and inversely proportional to area of cross section. More is the length of the wire, more will be the number of collision, more will be the resistance. Good. Then if more is the area of cross section, then more number of free electron can able to flow, so less will be the resistance. The microscopic form can be written as, right, we replace rho L by A by R. So I can write V equals IR. V equals IR. At constant temperature and other physical conditions remains unaltered, the current I through a metallic conductor varies directly as potential difference applied across it. At constant temperature and other physical conditions remains unaltered, the current through a metallic conductor varies directly as potential difference applied across its ends. So this is Ohm's law. Resistance. The resistance is the ratio of potential difference across the given conductor to the current passing through it. So this can be simply written as mathematical form R equals V by I. The SI unit of resistance is ohm, sigma. Then the dimensional formula of resistance is, so left hand side is or right hand side is V by I. V can be written as W by Q and W by Q divided by I. So I can have resistance equals W by IQ. So wherever you get dimensional formula of resistance, simply replace W by IQ and substitute the dimensional formula of W, dimensional formula of current, dimensional formula of Q. Then you start solving your problem. It's not necessary you need to remember the final dimensional formula of R. Let us work out that. R equals work dimensional formula is mL square T power minus 2 and current dimensional formula is A and charge dimensional formula is AT. After simplifying, the dimensional formula of R equals mL square A power minus 2 T power minus 3. Good. Let me go for the next topic, the reciprocal of resistance called conductance. The reciprocal of resistance is called conductance. The conductance equals 1 by resistance. The conductance is given by a formula G. Right? The SI unit of conductance is mho. Right? Sigma inverse. The dimensional formula is simply a reciprocal of dimensional formula of resistance. So I get m power minus 1, L power minus 2, A power 2, T power 3. Now let us learn about ohmic material. Materials or device that follows Ohm's law are said to be ohmic. So here we have an VI curve. There is a straight line which makes an angle theta. So now let us find the slope. Slope equals m, that is equal to tan theta. When we go with the formula, straight line formula passing through the origin, Ohm's law, right? This is a straight line passing through the origin, right? Then it is in the form of y equal to mx, right? So the slope m is simply resistance. So in VI graph is a straight line passing through the origin with a slope equals resistance. Remember this. So let me switch over from VI curve to IV curve. So I in the y-axis, V in the x-axis. Then there is a straight line, there is a theta. So slope equals m equals tan theta. Right? Good. Now the equation is I equals 1 by r times V. So I is in the y-axis, V is in the x-axis. Then 1 by r is the slope here. So in IV graph is a straight line passing through the origin with slope equals 1 by resistance. So in IV graph, if you want to find the resistance, then take the reciprocal of the slope. Non-ohmic materials or devices that do not follow Ohm's law are said to be non-ohmic. Here you have a curve. It is not a straight line curve. At any moment, its resistance will vary, right? Every voltage, it has a different resistance. A plot of I versus V for a non-ohmic material is a non-linear and they do not have a constant resistance. Ohm's laws cannot be applied for semiconductors, insulator, and solutions. Resistor. Here there is a symbol of resistor, a zigzag line is given, and a picture of resistor given with the color code. An object of conducting materials having resistance is known as resistor. An object of conducting material having resistance is known as resistor. Thank you, children.